Hello everyone, my name is Talip Ozturk. I'm the founder of Hazelcast project. So we're gonna talk about in-memory data grid, distributed programming, NoSQL a little bit today. Why Hazelcast? Because we all want to build highly scalable and highly available applications. So that's the goal. So Hazelcast is in production in many banks and telecom and gaming applications right now. So every second or so, one Hazelcast node will be starting right now in the globe. We all know hash map. So it's very simple. You put and get, but it's not thread safe. If you want to share this map across multiple threads, what do? We use what? Concurrent hash map. Now it's good to share the map. So what if you want to share the map across multiple JVMs, multiple nodes? Then we use Hazelcast. So Hazelcast will give you a map which is distributed, and then now you can any JVM running Hazelcast can share the map, and also the other data structures like queues and multi-map across the cluster. So I know demoing things a little dangerous, but I'll do it anyways. So I love taking risk. So let me go back a little. No, not this one, really. All right, desktop, Hazelcast. Okay. So if you unzip Hazelcast, you're going to see a directory like that. We have lib directory containing all the Hazelcast libraries. Hazelcast all jar is only jar that you need, really. It contains all the other jars. So just put that jar into your class path. That's it. Hazelcast doesn't depend on any other library or any other stuff. So just Java and Hazelcast all. That's all you need. So I developed. So also we have the management center WAR file to manage the Hazelcast cluster. I developed a command line application to demo Hazelcast. So I'll try that. Sage run sh. It's a demo application, as I said. It's a command line stuff. I'll type stuff. It will read my commands and try to make the Hazelcast API calls. Like if I do m.put 1 London, it's actually default map dot put keyM value. So if I do m.get, of course, map.get, I get the value. So if I start the same application, actually let's log in and see how it looks from the management center. All right. Connect. So it says you have only one member in the cluster, and you have a default map, and there's only one entry in the map. So let's start the other node. So let's go back to the bin directory. Sage run sh. It starts the second node. It will discover the other node, and from the cluster dynamically, we have 2-node cluster. If I type m.get1, I get the same value. So I inserted the value from the other JVM, started a new JVM, and new JVM can see the value. So if I go here, let me actually close and come back. So it should look a little better now. Okay, so I see the nodes, and I'll get the throughput soon. So if I put many, it's a special command to insert multiple things. So I will have more values in the. Okay. So all right. So we'll refresh now. Should have 101 total entries. So as you can see, it's distributed. So Some of the entries are here, some of them here, and also we have the backups of these entries on other JVM. So we extended the map a little bit so that we can have things like distributed locks and listeners. So I will lock the key 1 and try to update from here, m.put 1 New York. So I'm trying to override. But I won't be able to because the other JVM has the lock on the key 1. So, but watch what happens if I unlock. Of course, as you would expect, it will go through, and because it was waiting on the lock, it got the lock, and it was able to process the put operation. If I do get 1, I get it. So also let's see what happens really when I let me do it again. I get the lock 1. Let's go back here and see So now this tells me that there's 1 lock on this JVM. So you can see number of locks on the entries. So if you see, let's say you're running a highly an application with a lot of locks. If you see a lot of locks waiting here, that's a sign for you that you have a high contention on the map. So you have to worry about the locks that you're getting. So make that tell if you can also you will also see a warning if the lock is held for more than 5 minutes. That means you have a lock in the map that you didn't, or the system wasn't able to unlock for 5 minutes, which is a bad thing, right? So I'll unlock it and continue here. And if I can also add listener, so I'll add a listener. So this JVM will be listening for the map updates. So any JVM can update the map, right? So I'll update the map from here and say New York SF, and now that JVM received the event saying, hey, this member updated the map, and it's this is the key, and that's the value. So you received so this JVM received an event on the update. So Hazelcast also has other data structures like distributed queues, queue.take. So this JVM is trying to take something out of the queue. There's nothing in the queue. It's blocking. It's waiting for the items. So if another JVM says offer item, and then that guy was able to receive that item, just like any other blocking queue, but it is distributed across multiple JVMs. So we use the same Java util blocking queue interface in the Java. Okay, so let's go. Do you guys want to see anything here? Do you want me to try things here? Just let me know. So I can start another JVM, of course. Sage run sh. And that should connect, and we'll see that entries are rebalancing. So third node just came in, so we should see an update here. Now the keys are redistributed, so that we can have a high balanced cluster. Yes, same for the queue. So you can do poll for 5 seconds, 10 seconds. You can do a timeout. Yes. Good. All right. So let's continue here. So there are other. In our space, there are other solutions like coherence. IBM has extreme scale, Gemfire. Now it became Pivotal. It keeps changing. I'm not able to keep up. So Gigaspaces, Red Hat InfiniSpan, Grid Gain, Terracotta. These are all similar in the space, but we all have different things, so different feature set, license, cost, ease of use is very different. So I would highly encourage trying all of them so that you can love us more. So we looked at all that stuff and said, hey, that stuff should be open source. That stuff should be super simple. As a developer, I don't like complexity. Of course, inside you can have very complex things implemented, but I don't want to deal with that thing. So deal with the complexity. So internally, Hazelcast does very complex stuff, but it is hidden from the user. So for the user, it is just single jar. You put it into your class bed, and you start using the maps and queues that you already know. That's what it is. So that's why there's no dependency. It's a single jar, and it's not only a map, but it's also log, semaphore, topic, pops up messaging. So you can receive the membership events, who joined the cluster, who left the cluster, things like that. So everything is dynamic. You don't, as you saw, we repartition the data, so you don't have to interact with that stuff. We do the rebalancing, do the failover and all that stuff. So it is transactional. You can even secure the entire communication between the nodes, SSL or symmetric encryption. They're also supported, and they're all part of the open source free Hazelcast. So use cases. Anytime you say, hey, I've been running this application on one single JVM, one Tomcat or WebLogic, now I have to run it on 4, 10, 50 machines. So how do I write my application so that it will scale, right? So when it comes to scaling, you have to scale the state or data, right? So you're going to be trying to use NoSQL databases to scale your data store. Or also you have application state that you want to share across multiple JVMs. This is where Hazelcast comes very handy, right? So if there's an application state that you want to share, or if there are workflows that you want to distribute across multiple JVMs, this is where Hazelcast helps you. So if you have tons of data and you want to store everything in memory and process in memory, so that means you need more RAM, right? So since Hazelcast is partitioning your data, as you add more machine, Hazelcast will have more memory space to store things, and then you can run parallel processing on the data that you stored. So that's the idea behind Hazelcast. As you saw, data is not everywhere, so we're not replicating the entries all over the nodes. We're partitioning the data, and then taking backups, as many backups as you like per map. You can say, for this map, I want one backup, one synchronous backup, one asynchronous backup. For this map, I don't want any backup. So per map, you define how reliable you want to be, and same for the queue, of course. So how does it work? So like it's just, of course, you don't have to know any of that stuff, but it's always question how things work, and so that you have a better understanding of like internals of the tool, then you can optimize your application accordingly. So internally, Hazelcast has 271 default partitions. It's virtual stuff, virtual partitions. And the keys will be falling into these partitions. And so this is how you really find out the partition ID. We hash the key and mod with the partition count, which is static, right? So that means for a given key, we always have the same exact partition ID. So, and each node will know who owns which partition. So when you do a put, we're going to grab the key, hash it, mod it, and find the partition ID first and say, oh, this key is owned by that guy. So let me move the put operation to him so that he can process the put, take the backups. So backup is let's say first backup is another node. A backup will go to the other node and come back. So that's how it happens. The default backup strategy is synchronous. That means put will return after the backup. Of course, you can change that to become a synchronous backup. So let's say these are the own entries. So as you can see, I think this is blue color, right? So I'm colorblind. So as you can see, these blues are distributed really. Even backups are distributed. Can you, like, it's not like usually even in the NoSQL world, it's very common that one node will be backup of the other node. It's very common. But we didn't do it this way. We did it in a way that it is, even the backups are distributed. Can you think of a reason why we did it this way? So why would you want to have the backups even distributed? What would be the benefit?
So if the main node goes down, then the load spike on the backup.
So that deserves a book, definitely. Yes. Thank you. That's exactly what it is. So when a crash happens, you don't want to deal. You want to make sure that the cluster is already in a balanced state. You should not be doing anything else. So when this node dies, just imagine this being crashing. So you already have the blues are like partitioned and balanced already. There's nothing to do. It's already balanced. So you design everything with the idea that things are going to crash, and you're ready for that crash. So if we add a node, what do we expect to happen? Of course, we don't want this guy to sit down and do nothing. We want this guy to take some of the loads. So and that we call this migration. Some of the partitions will migrate to that node. Eventually, you were going to have balanced cluster again. So we have three types of discovery. One, which is the default multicast. That's what I used in the demo. That's how they discovered each other. The second one, TCP/IP. So you have to list the number of well-known addresses. Not all of them, but some of them should be there so that we can connect to the cluster over the known members. And the third one is if you're running the application on Amazon EC2, we have an automatic discovery for Amazon EC2. You don't have to declare anything. You just say, this is my Amazon credentials. Just go find the members. So yes. So of course, bad things will happen. Node will go down. You'll lose a node, and we should be able to restore from backup, and eventually even balance the backups. As of 3.1, we'll let you do the partitioning, so you will assign the memberships and everything. You can assign, but that's also very super dangerous. So it's like only super experienced people should be doing it, because you can mess up the whole thing, right? So if you do repartitioning all the time, you can kill the network. So things like that. So we give you that power, but we're still not sure if we should, because like you can. So one of the things actually about this tools like that, Hazelcast, like if you look at the API, you're going to say, oh, I know all that stuff, the queues and maps and the multi maps. I get it. It's super simple. And you start using it, right? So you start in and out, like the Executor service and the logs and the transactions, because it is easy. So you'll be motivated to do all that stuff, and you can create a mess out of this. So why? Because yes, it is super powerful, but it is also super dangerous. That you can actually, this is true for a lot of stuff, right? So a lot of powerful things you can. So you can mess up things quite well. So what we should be thinking, it's like first time when JDBC or programmer starts doing JDBC stuff, right? So the database, So he can create, or she can create terrible SQL statements and like kill the database, right? So then you learn like, oh, you know what, I have to do the indexing, or I have to order my query criteria and blah, blah. So you learn. So the same goes for this thing too. Like all that distributed stuff, very new to a lot of people. Even a lot of, you're all smart, but still, it requires a lot of experience, right? So it's like, you say, let's say you do a lot of queries. So because it has a query capability, you say like, all right, I'll do indexed map, and then I'll do a lot of queries. Then you have to feel that it is actually expensive stuff. So when you do a query runs on every node and comes back, and then combines the results. So it's an expensive operation. So you see the log, and you start thinking, hey, I can lock and then do my operation and unlock. So it looks very easy and attractive, but eventually you're killing it. So that's, we should be a little careful about. So I was always questioning that decision. That's what I'm trying to say. So anyway, if you look at the, oh, doesn't look nice. But so these are data nodes in the cluster. You have to, we recommend to run the Hazelcast cluster on a highly reliable and fast enough network. So it should not be like one node here and one node another across the internet somewhere else. So it should not be like that. So it's designed to run on a reliable enough and low latency enough network. So, and these are data nodes with the dots, and these are called light member with no data. So it's part of the cluster. They're members of the cluster, but they don't hold any data. So you can do processing there, but you cannot do, it doesn't hold data. Let's say this could be your Tomcat applications, and these could be your data storage nodes. So let's say you want to separate the data from the processing. And these are clients, native clients. Could be Java, C#, and hopefully next release we're going to have C++ client. So in an enterprise edition of Hazelcast, which is like 95% of the Hazelcast will be all free, all that stuff you saw, all free stuff. In an enterprise, we'll have elastic memory storing things off the heap so that garbage collection will not kill you. So, or advanced security, JAWS-based security, or management center, these are all part of an enterprise. So I'll skip that part and come to the Hazelcast open source. So you can actually create as many nodes as you like on a single JVM. So as you say, Hazelcast new instance, it will give you an instance. So now with the same configuration, we have 2-node cluster right here. So you can even write a JUnit test with that. Like you can start 5-node cluster, right, on the same JUnit test, and then say, I'll put from here, try to get from there, and see if we'll lock from there, and try to update from there, and see if it works. So actually, our functional tests will use that functionality. So you can create as many nodes as you like in a single JVM. Yes, we rely on serialization. Somehow we should be able to serialize the object, somehow. Either the object should be serializable, or you tell us how to serialize it. Or if you want to have faster serialization, you go with data serializable interface that we have. You have to implement a couple of methods here, 2 methods actually, and then the serialization will be much faster. With the version 3, we came up with the portable serialization, which means you can serialize from any language to any language, C++ to Java, C#, and actually it supports the versioning. So if you change your value object, you edit a field, you don't have to reboot the entire cluster. It will say, oh, that's okay, I'm good with new fields in the cluster in the object, or you can remove a field from the object, and it will still work. And also another good thing about the portable serialization is that, let's say you serialize a big object, and all you want to do is reading a field out of that object. Normally, reading means Of course, we convert the object into byte array so that we can pass it around, right? So the network. But when it comes to reading, we have to give you the object and you do a get on that object, right? Or with the portable serialization, we don't have to deserialize. We can give you exactly the value that you field that you need. So we scan the byte array, find exactly where your price value field is, and just read the 8 byte and give it to you. So we skip the serialization that way.
Did you use open source portables?
Yeah, it's all open source, yes. Yes. Okay, so as I said, you can listen for the membership events, very simple API, and get the set of members in the cluster. Put if absent, replace, all good. Yeah, timed operations like poll 5 seconds. So you get the time. So you can get a null if there's nothing. So all blocking operations. Locks. These are global locks. These are the locks in the individual map. So these are you're locking the map entry actually. So we did it in the demo, right? So default map.lock key. This is exactly what it is. And the good thing about this one is that if there's no value associated with the key, when you unlock, we remove the entry. So it's auto garbage collection for you. So you don't have to explicitly remove the key. All right, so topic, like a JMS topic, very simple. You listen for the members, the messages. Anyone can publish. If we're talking about the same topic, so whoever listening will get the published message, basically. So publish and receive. That's it. Very simple. So idea was that, hey, you already formed the cluster. You're already sharing stuff. You can share the queue. Also, you can do messaging like that, right? So.
Is there a big performance improvement compared to JMS topics and queues?
So let's talk about the queue first. The version 3 is designed to scale very well when it comes to queues, because each queue will be sitting on a different node. So if you have 1,000 queues, so you distributed the queues. So just imagine doing that with the JMS, right? So you're talking to the exact same instance for all queues. That should not happen. The Hazelcast will shard the queues. That's a good performance thing. So it scales amazingly well. So as you add more nodes, you can have as many queues as you like. It will scale just fine. So, but if you're talking about one queue, not sure. I didn't do a testing for like compare. So the purpose wasn't really like converting or replacing JMS queues. The idea was that 90% of the time, what you want is you have the cluster, you just want to do queuing and like messaging, right? So this is, and that's usually what you need, and this will give you that. So if you really want like a persisted topic, like so you can have that with the JMS implementations. So you may still need to use JMS implementation, but 90% of the time you're going to see that this is fast enough, capable enough, and much easier, right? So that's what it is. And if I so 80% of our Hazelcast users are using topic and queue actually. So we actually started with the queue first. So the first implementation was queue and then map, and then we kept adding. So yes, events. You saw that we can add a listener for the entire map or for a particular key, and then as updates happen, you'll get notified. So that's very simple. So. Okay, so task, the executor service. you know the callable stuff from Java util concurrency package. So you run the callable or runnable across the nodes. So you can say, hey, execute on, this one is actually better. You can execute on a specific node. This node, I want this node to run the thing, or any available. I don't care. Just run it somewhere, or a defined number of nodes, or all of them, or per key. You can say, go to the owner of this key and run it there. Why? Because my data is there. So data locality. That's what you want to achieve. So your process will go to the owner of the key and run there. So okay, let's work on an example. So let's say you want to remove an order from a customer, and this is usually what you would do. You get a customer's map, you lock it so that no one is touching that customer right now. You don't have to, but let's say your business requires that level of security, okay? So you lock the entry, get the customer, remove it, put it back, and unlock. Looks very simple, but it's dangerous. Why? It's not dangerous, but it's very expensive. Why? Because you have 4 distributed operations there: lock, get, put, and unlock. So it looks very simple on paper, but it does a lot of stuff. So how can we optimize that? So create a task which is partition aware, and say that the partition key is actually the customer key. If you execute that task, he's going to say, oh, this is partition aware. Right, so what's the partition? Customer ID. Okay, I'll go to the owner of that ID and run the task over there. It will be local, but still not super well. I mean, this is better than the other one, but still, like, this is still expensive. Why? Because even if you run that stuff locally on the node, yes, the owner will be local, but the backups are not really local, or even the lock will still be required. And lock means you still have to lock it here, and the backup, you still have to unlock here and the backup. Still not that cheap. Cheaper, but not the cheapest. So if there was okay, let's try to become a little more creative. So how can we even just forget about what Hazelcast can do, but just imagine just try to come up with a way to eliminate that. So what do you think Hazelcast would have done to even get rid of that thing? Make it even super, super cheap. If we can somehow get rid of the locks, right? So if we can somehow guarantee some atomicity for the operation, then we are super fast, right? So no this, no that, only get, which is local, and put, so local and backup, cheap as possible.
Transaction, make it like transactional and have it.
But still, transaction means lock. So that was the answer. So get rid of the lock somehow. So how do we get rid of the lock? So Hazelcast 3 has something called execute on key. So if you can come up with a task like that and execute on the key, and if Hazelcast can guarantee the atomicity, then you're good to go, right? So you don't have to lock anything. So version 3, try to remember that. So execute on key is a super, super powerful tool. So that means, so if you want to execute on the entries, you can have thousands running per node, right? And they have nothing to do with each other. There's no lock expense. It's super free. Just go there, run there, and run and just get out. While you're running, it's all yours. You get an implicit lock for the entry. Entry is yours. Do whatever you want to do. While you're touching, it's guaranteed that no one is touching, and then get out. So what else is good about that? Since you have the entry, since you have the process running on the entry, so you don't have to bring the data, process, and then put it back. If the object is big, that's super expensive, right? All you're going to do is actually just changing a couple of fields. So you just want to go there, process something, change a couple of fields, and just get out. So entry processor. So just remember that. Yes?
If it's an implicit lock, how is it implemented? How does Hazelcast make it super fast?
We have internal threads executing all the commands actually. And we assign it. So per partition, we know which thread should be running that process. So we take your process, go to the owner node, and find the thread that should run the execution, and run it there. So I don't have to deal with the lock anymore. I know that that thread is responsible for that partition. While you're touching, no one can touch it anyways. So the thread is yours. Just go and run and just get out. That's it. That's how we do it. Yes. So persistence, we don't persist, but we will let you persist. So if you have map store, map loader implemented, so when you do a put, we'll call you your store method. You save it into somewhere. If you try to do a map.get and the value is not there and you have this defined, we'll call you to load it from the storage. So that means you can have a big giant storage and you only cache some portion of it. So write can be asynchronous or synchronous. So that means it could be part of the put. Means map.put will return after storing, which is synchronous right through, or the second one right behind, which means put will return immediately, but it will mark the entry as dirty. So every 5-10 seconds you define that. Hazelcast will scan the dirty records and just flush it to the storage. So yes, it's a distributed implementations of all that good stuff, and we do have clients. So I don't want to. So I want to have at least 5 minutes for the questions and then close the session. Thank you so much for coming and listening. Hope you enjoyed it.